Hello. Today we are going to discuss Chapter 3, which is displaying and describing categorical data. Remember that categorical data is data that's not numbers. Whether you're a night owl or an early bird, whether you like sweet or salty, what kind of social media do you use? Those are categories, and therefore it's categorical data. We're going to use the survey results that are in the module under today, which I don't know what day it's under, but there are the survey results in there, and I suggest you get those out and look at them. You should be pausing the video, tallying things up, and I'm going to tell you when to do that. So it's kind of more of an interactive video. You should be working with your Chapter 3 handout. So you want to get that handout printed and then or pulled up on your device and take notes on it, just like if you were sitting in class with me. So when we talk about describing and displaying categorical data, frequency is important, how often the variable occurs. And we're going to look at the frequency first of social media use, and we'll create a frequency table. Now when they ask you for a relative frequency is asking for the percent. And percents are a lot more useful to compare with because they give us an absolute, a way to compare. Comparing 20 to 35 is not as effective as comparing 25% to 35% because we have a frame of reference there. So the distribution is all the possible values a variable can have and its frequency. Contingency tables are tables that display the counts, sometimes percentages of individuals falling into the named categories on two or more variables. The table categorizes individuals on all the variables at once, and we're going to make one of those today. And then when we have a contingency table, we look at the marginal distribution, which is the margins. Okay, so let's look at marginal is margins and the totals, okay, of that distribution. Now the conditional distribution is where we limit the who. We limit it to one of the variables and one of the categories within that variable. So if the table is the gender, we maybe only want to look at females. If it's night owl or early bird, maybe we want the conditional distribution of night owls, whether they like sweet and salty. So the conditional distribution looks at one row or one column. Two variables are considered independent if one variable doesn't affect the other. And this can be calculated numerically, and it can also just be kind of an idea. When we look at probability, the idea of independence is if I'm rolling a die, each event is independent of each other. But it's harder to determine if your sleeping habits are independent of your food choice. And so you look at whether or not they are the same, whether the probability of it happening or the percentage of time it happens is the same amongst different variables. So when we look at gender and voter preference, we see that there isn't independence there, and they call this the gender gap. If the two are independent, then the percent of males voting Republican will equal the overall percent voting Republican. Or you can look at them several different ways. The percent of males voting Republican will equal the percentage of females voting Republican. This isn't usually the case, and nowadays it's definitely not, and they call this the gender gap. And then we're going to talk about Simpsons Paradox at the end, and that's when averages are taken across different groups. They can appear to be contradictory. And like I said, we'll talk about that at the end. Now, there's also the area principle when it comes to graphs, and it's that a statistical display is usually some kind of graph, a bar chart, a pie chart. We'll talk about histograms and scatter plots later on, a time plot. Each data value needs to represent the same amount of area. So your area has to be representative. And if you look in your textbook at the end, there's some pictures of Titanic. And that it really gives a good illustration of the area principle, kind of misleading the graph. So bar charts are, the bars represent the count of each categorical variable, and the bars do not touch. Now there's also a histogram in which the bars do touch, and so that's used for quantitative data. And then there's pie charts, which you have seen. Each portion is a wedge, and pie charts are really easy to make in Excel, but not so easy to make by hand. So we choose
Contingency table so we know how large each of our bars need to be. So we have Twitter, we have Snapchat, we have Instagram, and we have TikTok. Oops, I'm old. I spelt it correctly. Facebook. It's good to see there's still a few young people on Facebook. It's not just all old people. I'm not on Facebook. And did I get them all? Yeah? Okay. So, if your birthday is in January, I need you to go through this list and count up how many people are on Twitter. If your birthday is in February and March, I need you to count how many Snapchats there are. If your birthday is in April and May, I need you to count Instagram. If you're in June and July, you need to count TikTok for me. I can't divide you by rows or tables, so we'll use birthdays. If you are August, September, oh, there's 6. August, September, count Facebook. October, November, count Pinterest. If you're December, also count Twitter. And then we can report out the numbers, and then we can make our graph. Is my connection better now? All right, I think it was because I had too many devices pulling from far away. All right. I need you to unmute and tell me how many. Did we get it all yet? 31 for Instagram, 8 for Facebook, 10 on Pinterest, 7. Okay, I was like, that's really low. And Twitter. All right, does everybody agree with these numbers? Okay. Okay. All right. Perfect. Okay. So we're going to. I need to write these down so I don't have to keep switching back and forth.
do what's called a segmented bar graph instead, and I'm going to show you how to do that. So we're going to start by using our data, and we're going to make a tally of the social media use for our class. This is the data that I gathered for the first week of school. Now, what I want you to do is pause the video right now, and I'm going to pause my recording so there's not like 10 minutes of me tallying everything up. And I want you to put a tally mark for each person that says Snapchat and Twitter. And this isn't going to add to 100 because people are adding in more than one category. So I want you to take a second and pause this so that we can make our bar chart. Okay, so I have tallied up the social media use for our room. We're at 18 Twitter, 30 Snapchat, 34 Instagram, 29 TikTok, 2 Facebook, 22 Pinterest. It's always interesting year to year to see how this changes. I think the last couple of years, Pinterest and Facebook had very, very few. Now Pinterest has 22. And at one point in time, Twitter was huge, and Instagram wasn't. And now it's funny how it flows. So we're going to make a table. And if we were in class, I'd be making a cute poster. But of course, we're not. Well, I'm not. And I'm counting down the days until I'm allowed to return because I am bored in the house bored. I'm going to show it to you here, okay? And you can see that this is our data, and I'm going to tally this up, okay? All right, so we looked at this, we added it all up. I'm not sure if this going back and forth the slides is going to be a weird video. It might not make sense. We'll see. So we're going to make this bar chart, and it needs to go up to 35. So 5, 10, 15, 20, 25, 30, 35. Okay. And then we have Twitter, Snapchat, we have Instagram, and TikTok, Facebook, and Pinterest. So Twitter is at 18, so it's about here. And Snapchat is 30. Right, so this is the bar chart you made like in elementary school, middle school, when you're asked to display some data. 29 for TikTok, 2 for Facebook, 22 for Pinterest. Okay, so there's your bar graph of our classes' social media use. We can see that Instagram is the most prevalent, with Snapchat being next, then TikTok, and the size of the bars are what tell us that. So the next thing we're going to look at is our sweet and salty fit in early bird, late night owl, or the neither. So a contingency table is where we're going to sort these on the different variables. So what I'm going to do is I'm going to, in my Excel document on my computer, is I'm going to sort by the sweet and salty first. Then I can count up how many night owls are each one, and then let's see, that didn't work. And it's just going to make it easier for me to count here. So I have all the salties. On the top, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 salty. Those Those are my totals. And of those salty, I had 2 early birds. I have 1, 2, 3, 4, 5, 6, 7 neither. And I'm going back to that Excel document and I could sort it, and that's what's helping me get this faster. But I'm looking at it on my computer, not the iPad. And I'd be making you count this yourself if we were in class. So I have, does that add to 21? Yes, so we have 2 early birds, 12 night owls, 7 neithers for the 21 total people who prefer salty. And then for sweet, we have 1, 2, 3, 4, 5, 6, 7, 8 early birds. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 night owls. We have 0 neithers for a total of 17. And that gives me 38 total. And then we fill in our totals here. 7 plus 0, 12 plus 9 is 21, and then 10. So there is our total. We have 38 respondents in class. Somebody only answered one of the questions, so we didn't get all 39 in here. So now that we have the contingency table made, when we talk about conditional distribution, you're talking about, that's what I meant to do. One, maybe we're looking only at the conditional distribution of the night owls, or the conditional distribution of the sweet people that prefer sweet. If we ask for marginal, we're looking for the totals. Okay, we're looking at the totals when we're asked for the marginal distribution. And hopefully you're going to get your calculator soon. When you check out your books, you should be getting your calculator, but these calculations can be done with just a basic calculator. So let's make some room for some of these calculations here. What percent of the class? Okay, so some of the questions you're going to be asked are going to be looking at, it's going to sound like the same question, but you're actually asked for something different each time. So what percent of the class? So that means our denominator is going to be the whole class, 38. Are sweet and night owls. So we want to look for the people that are sweet and night owls. So that's 9 out of 38. And then the marginal the relative frequency would be that percentage, 9 out of 38. And so if it asks you for the relative frequency, you give the percentage. Obviously, it's asking me for the percent here, so we also are going to give the percent 0.0237. And we always want 3 numbers behind the decimal, not including leading zeros. Okay, so in science you would call that sig figs, but we don't do the whole sig fig calculation. It's just 3 good numbers behind the decimal point. So what percent of night owls prefer sweet? So now we're looking only at the night owls, and so our denominator becomes 21. How many of them prefer sweet? Well, that is still 9. So we can see the question is asking me for the same cell, but the denominator changes. So 9 out of 21 is 42.9. 0.429 or 42.9%. You don't get marked off if you're asked for a percent, and you actually just leave it as a decimal. What percent of those that prefer sweet? So what percent of the sweet, that denominator is a 17, are night owls. So again, that numerator is also 9. So you can see that the different questions are asking me about the same cell, but each time it's giving me a different denominator depending on what the question is asking. So that's 9 out of 17, and that's 52.9%. Okay, now if it asks me for the marginal distribution of sleep habits, okay, so the marginal of sleep habits, I want the margins of the sleep. So that's 10 are early birds, 21 are night owls, and 7 are neither. If it asks for the marginal relative frequency distribution, then you're going to convert all those into percentages over 38. Now the conditional distribution of food choice among early birds means I'm going to be looking at food choice among early birds, so just these numbers. Okay, so the conditional distribution here would be 2 like salty and 8 like sweet. And again, if it's a conditional relative frequency distribution, you would do 2 out of 10 and 8 out of 10 and turn those into percentages. Our food choice and sleeping habits independent for our class. So we can look at that and see we have 8, we can pick any of them. So what percent of the early birds like sweet? Well, that's 8 out of 10, right? 8 out of 10 early birds like sweet, but 17 out of 38 in the whole class like sweet. If those percentages are equal, then we're looking at something that's independent. But 17 out of 38 is 44%, and 8 out of 10 is 80%. So these are not equal. So because the percentages are not equal, sleeping habits and food choice are not independent. They would need to be the same, and that would tell us that the sleeping habit didn't affect whether people like salty or sweet. So that is how we look at that. And we could also compare it, like the 8 out of 10, we could compare that to the 9 out of 21. Well, that's also not the same percentage. So we can again say that they are not independent. You can look at any of them, any two percentages. If they're equal, then independence can be assumed. But if they are not, then we cannot assume independence.
Which is, oh, what did I just do?
Okay, so again, if I was in school, I would have M&Ms for you, and we would get out a bag of M&Ms, and we would count the plain and the peanut and the color distribution, and then we would get to consume said M&Ms. But alas, we are not here, and I am not able to go out and buy a bag of M&Ms to even demonstrate this with. So I'm going to use the data that I used last year. So last year I had a bag of plain M&Ms and a bag of peanut M&Ms, and I was the only one partaking on camera. And we had in our plain M&Ms, we had 9 red, 25 orange, 18 yellow, 22 green, 23 blue, and 4 brown. This is a frequency table for the plain, and then we had this frequency table for the peanut. So a frequency table is just a table in which we list the frequency of different categories for a variable. In this case, it's the color and the type of M&M. When I put these two together, I put it into a contingency table, and I have all my totals. So I have the contingency table for the type of M&M and the color, and then the totals. Okay, so again, the totals would be my marginal distribution of color, or my marginal distribution of the number of M&Ms in the type of M&M. But we are going to create what's called a segmented bar graph. We want to know what percent of each of these, of the bag of M&Ms is each color. And M&M actually used to have a color distribution published, and we use the old color distributions a lot of times to make comparisons. But with a segmented bar graph, we're going to look at the percentages. So I'm going to convert everything here to a percent. And then we're going to make a bar chart that stacks the percentages on top of each other so that the bar is 100%. So I'm going to pause it for a second and calculate these percentages. And I would like you to do the same. Pause it, calculate the percentage of plain M&Ms that are red, orange, yellow, green, blue, and brown, and same for peanut. And then we will continue. and I'm good. I unpaused it for a sec because I'm going to round it. 8.9% is going to be 9%. These are pretty much going to end up being 9.25 and so on, because it's going to be too hard to graph actually 24.7%. Okay. Okay, so I've calculated the percentage of peanut M&Ms, and remember I did round just because on a graph that you're drawing by hand, drawing 11.7% is not going to be very accurate, so you might as well just pretend you're drawing 12. And I'm going to add it up and make sure I get close to 100. My rounding. Yeah, see, I got 101. So one of those should probably be rounded down instead. But it's close enough. All right, so this is how we start our bar graph. We have two bars, one for plain and one for peanut. Okay, the bar represents 100%. So here we have the type of M&M, and then we have the percent on the side. And then we're going to color in each portion for the percent of this bar that makes up the M&M. So think of it like filling up a jar with the M&Ms. First you pour in the red M&Ms, and those are going to be 9% for the plain. So I'm going to draw this line. I'm going to color in my 9% for the plain. And for the peanut, it's 12, so slightly over the 10. And then we'll color that in. Now we're going to pour in our orange. And I'm going to try to get a good orange here. So I have 9% plain, and I'm going to pour 25% orange on top of that. So that means this line is going to go up to the 34. Okay, so it's going to go up to 34. Oh, I thought I changed that to orange. There we go. Right, so this represents 25% orange, and we added that on top of the 9% red. And then we have another 12% on the peanut that's orange. So 12 plus 12 is going to give me 24. And we're going to add that on top. So now we're at 24 total, right? So you're pouring the colors on top of each other, and the percentages are stacking up. Okay. Next is the yellow. Yellow adds 18% about. So we're at 34 plus the 18 is going to take me to about 52% when I add in that 18%. And that's the yellow. And then I'm going to add, the peanut was 29% yellow, so I have 24 plus the 29 puts me at 53, so just above the other one. And we can see visually the color distribution really well with these. And then when they're side by side, we make sure we do the same order of how we stack stuff in the bars, and then it helps us to make comparisons visually. So we're at 52% on the plain, and we're going to add 22% green. Okay, so 52 and 22 is 74. Green. And then we're at 53%, and we're going to add 12% green. So 53 plus 12 is 65. And then blue adds 23% to that. We're at 74. Yeah, 74 plus 23, 97-ish. So 97-ish. And then that last 4% is the brown. And then we are adding 21% blue to 65, so that's 86. And then the last 15, 14%-ish, remember we're off by a tad, is brown. And there's our brown. And so there is a visual display called a segmented bar graph of the distribution of peanut and plain M&Ms. And now if you're asked to compare the distributions, you want to talk about more and less, bigger, smaller. So the plain M&Ms have a larger percentage of orange than the peanut does. And the peanut M&Ms has a larger percentage of yellow and brown than the plain did. And so when you're asked to write a description of the distribution, you want to compare each color and say one is bigger, one is smaller. It's about the same. It's bigger, right? The orange is larger in the plain. The peanut is larger in the yellow. The green is larger in the plain as well. The blue is about the same, 23 and 21%. The brown is larger in the peanut. And make sure when you're talking about comparing two things, you use those comparative words, bigger, smaller, and so on. So the last thing to talk about for chapter 3 is Simpsons Paradox. Simpsons Paradox is what happens when you take averages and you combine all the data together. And really, it's better to look at things separately. So here are two baseball players, player A and B, and their overall batting percentages or batting proportions. It's the last inning of an important game. Your team is a run down with bases loaded and 2 outs. The pitcher is due up. So you'll be sending in a pinch hitter. There are 2 batters available on the bench. Who should you send in to bat? Well, if you look at these percentages just the way they are, player A has a 32% batting average, and player B has a 29.8% batting average. So it's maybe a better idea to send in player A. But there's other things that affect batting. And we would probably be having a discussion, and I'd be looking for someone who plays baseball to give me some information about what are some of the things you consider when you are putting a batter in against a pitcher. And one of them is whether the pitcher is right or left-handed. And so if we look at the percentages across different pitchers, righting and left-handed, we get different information. So remember, this player A looked better with a 32% batting average. And now let's look at player A against the left-handed pitcher, 28 out of 81. And that's 34%. And 5 out of 22, that's 22%, 22.7. And then 12 out of 32 is 37.5%. And 33 out of 119 is 27.7%. So when we look at the individuals and we look at the pitchers and we separate it instead of grouping it all together in one, because pitching is the handedness of the pitcher is an important part of baseball. When we take that out and average it all together, we lose important information, because when we separate it, we see that batter B is actually better against both sets of pitchers, but for some reason his overall average is lower. And so that is the paradox that happens when you combine data that should be separated. And so it happens because here's like a slide rule. Your average, depending on how many of each pitcher you hit, can slide anywhere in between the two individual averages, your overall average. And so this overall average tends to be a little bit lower, and his overall average the B tends to be a little bit lower because maybe he hit more of the right-handed pitcher, and this guy's maybe a little bit higher, and so they can cross over sometimes and overlap when we average things together. So the important information to understand here is that it's important to divide the data up across important variables so that we get the whole picture. And that is Simpsons Paradox. And the same thing can happen with companies and salary. I'm not really going to get too much into this example, but that wraps up our chapter 3, and I apologize for it being so long.